Hi, welcome to the COSI 137 lecture. Sunny here. For this module, we will talk about performance. Let's start. Signal travels through transmission media, which are not perfect. The imperfection causes signal impairment. This means that the signal at the beginning of the medium is not the same as the signal at the end of the medium. What is sent is not what is received. Three causes of impairment are attenuation, distortion, and noise. Attenuation means a loss of energy. When a signal, simple or composite, travels through a medium, it loses some of its energy in overcoming the resistance of the medium. That is why a wire carrying electric signals gets warm, if not hot, after a while. Some of the electrical energy in the signal is converted to heat. To compensate for this loss, amplifiers are used to amplify the signal. To show that a signal has lost or gained strength, engineers use the unit of the decibel. The decibel measures the relative strengths of two signals or one signal at two different points. Note that the decibel is negative if a signal is attenuated and positive if a signal is amplified. Example: suppose a signal travels through a transmission medium and its power is reduced to 1/2. This means that P sub 2 is 1/2 P sub 1. In this case, the attenuation can be calculated as follows. A loss of 3 decibel is equivalent to losing 1/2 the power. Another example. A signal travels to an amplifier and its power is increased 10 times. This means that P sub 2 is equal to 10 P sub 1. In this case, the amplification can be calculated as follows. Distortion means that the signal changes its form or shape. Distortion can occur in a composite signal made of different frequencies. Each signal component has its own propagation speed through a medium, therefore its own delay in arriving at the final destination. Differences in delay may create differences in phase. The delay is not exactly the same as the period duration. The shape of the composite signal is therefore not the same. Noise is another cause of impairment. Several types of noise may corrupt the signal. Thermal noise is the random motion of electrons in a wire, which creates an extra signal not originally sent by the transmitter. Induced noise comes from the sources such as motors and appliances. These devices act as a sending antenna, and the transmission medium acts as the receiving antenna. Crosstalk is the effect of one wire on the other. One wire acts as a sending antenna, and the other as the receiving antenna. Impulse noise is a spike, a signal with high energy in a very short time, that comes from power lines, lightning, and so on. The signal-to-noise ratio, or SNR, is defined as average signal power over average noise power. SNR is actually the ratio of what is wanted to what is not wanted. A high SNR means the signal is less corrupted by noise. A low SNR means the signal is more corrupted by noise. Because SNR is the ratio of two powers, it is often described in decimal units. A very important consideration in data communications is how fast we can send data, in bits per second, over a channel. Data rate depends on three factors: the bandwidth available, the level of the signals we use, the quality of the channel. Two theoretical formulas were developed to calculate the data rate: the Nyquist bit rate for a noiseless channel, and the Shannon capacity for a noisy channel. For a noiseless channel, the Nyquist bit rate formula defines the theoretical maximum bit rate. The Nyquist formula tells us how many signal levels we need. Increasing the levels of a signal may reduce the reliability of the system. Example: what is the maximum bit rate of a noiseless channel with a bandwidth of 3 kHz transmitting to signal levels? Using the formula, we got 6000 bps. Another question: how many signal levels are needed to send 265 kilobits per second over a noiseless channel with a bandwidth of 20 kHz. Using the formula, we get 99 levels. In reality, we cannot have a noiseless channel. The channel is always noisy. In 1944, Claude Shannon introduced a formula called the Shannon capacity to determine the theoretical highest rate for a noisy channel. Note that in the Shannon formula, there is no indication of the signal level, which means that no matter how many levels we have, we cannot achieve a data rate higher than the capacity of the channel. In other words, the formula defines a characteristic of the channel, not the method of transmission. Sample: a telephone line has a typical bandwidth of 3000 Hz for data communications. SNR is 3162. What is the capacity? Using the formula, get 34,860 bits per second. In reality, both methods are used to find the limits and the signal levels. Example: we have a channel with a 1 MHz bandwidth. The SNR for this channel is 63. What are the appropriate bitrate and signal level? We use the Shannon formula to find the upper limit, and we get 6 megabits per second. Shannon formula gives us 6 megabits per second, upper limit. Better performance, we choose something lower. Let's say we use 4 megabits per second. We use the Nyquist formula to find the number of signal levels. One characteristic that measures network performance is bandwidth. However, the term can be used in two different contexts with two different measuring values: bandwidth in Hertz and bandwidth in bits per second. Bandwidth in Hertz is the range of frequencies contained in the composite signal or range of frequencies a channel can pass. The term bandwidth can also refer to the number of bits per second that a channel, a link, even a network can transmit. There is an explicit relationship between the bandwidth in Hertz and bandwidth in bits. Basically, an increase in bandwidth in Hertz means an increase in bandwidth in bits per second. The relationship depends on whether we have baseband transmission or transmission with modulation. The throughput is a measure of how fast we can actually send the data through a network. Although at first glance, bandwidth in bits per second and throughput seems the same, but they are not. The bandwidth is a potential measurement of a link. The throughput is an actual measurement of how fast we can send data. Latency or delay defines how long it takes for an entire message to completely arrive at the destination from the time the first bit is sent out from the source. We can say that latency is made up of four components: propagation time, transmission time, queuing time, and processing delay. Propagation time is the time required for a bit to travel from source to the destination. It is equal to distance over propagation speed. Transmission time is the time to transmit all the bits. It is equal to the message size over bandwidth. Queuing time is the time to hold the message before it is processed. Question: what are the propagation time and the transmission time for a 2.5 kilobyte email if the bandwidth is 1 gigabits per second? Assume the distance between the sender and the receiver is 12,000 kilometers, and light travels at 2.4 times 10 raised to the 8 meters per second. Bandwidth and delay are two performance metrics of a link. However, what is very important in data communications is the product of the two, the bandwidth delay product. It defines the number of bits that can fill the link. In this example, the bandwidth is 1 bits per second. The delay is 5 seconds, so the bandwidth delay product is 5 bits. Another example, here The bandwidth is 5 bits per second, and the delay is 5 seconds. The bandwidth delay product is 25 bits. We can roughly say that jitter is a problem if different packets of data encounter different delays and the application using the data at the receiver side is time sensitive. If the delay for the first packet is 20 microseconds, the second packet is 45 microseconds, and for the third packet is 40 microseconds, then the real-time application that uses the packet endures jitter. That ends Module 6. Thank you.